In this section, we are going to do an introduction to hypothesis testing. So this is going to go over a lot of the terminology that we're going to need in hypothesis testing, and it's not going to go over a lot of the actual mathematical processes of hypothesis testing. So hypothesis testing is the process of assessing evidence provided by a sample of data in favor of or against a claim about the population. There are 4 steps to hypothesis testing. The first step is to state the claim. There are always 2 claims in a hypothesis test. The first claim is called the null hypothesis test. The null hypothesis. That is a statement of no difference between the variables, so they're equal. This can often be called or considered the status quo hypothesis. So it's things are staying as they were. We denote the null hypothesis as an H with a subscript 0 next to it, or HO. The second claim is the alternative hypothesis. This is a statement contradictory to the null hypothesis. This is the statement of what we want to prove. We are collecting our data to provide evidence towards this claim. The alternative hypothesis can be denoted as an H with a subscript A or an H with a subscript 1. In my notes, I tend to use the H with the subscript A to note the alternative hypothesis. The second step for hypothesis testing is to choose a sample and collect the data. So notice we are creating the hypothesis, the null and alternative, before we collect the data. So just like in a science experiment, you create your hypothesis and then you perform the experiments. Same thing here. We're going to create the hypothesis. We're going to come up with the thing that we want to prove. Then we're going to go out and collect our data. This is also the step where we would perform any descriptive statistics. So we would create tables, graphs, charts, all of those things in this second step as well. If we look at the data and all of the descriptive statistics, and the data does not support our alternative hypothesis, that's where the process stops. If we think that the proportion of people that prefer chocolate ice cream over any other flavor should be more than half, and we go out and we take a sample of people and our sample proportion is less than half of the people said they prefer chocolate ice cream, then we don't need to continue on because we said, I think it's more than half, and our sample says, actually, it's less than half. We don't need to continue. We're done. If, however, the data does appear to support the alternative. So I said, I think more than half of people love chocolate ice cream, and that's their favorite. And I go out and I find that 60% of my sample picked chocolate ice cream as their favorite. This does not mean that my hypothesis is correct. Instead, it means that I can proceed on to the third step. The third step of the hypothesis test is to actually perform the hypothesis test. It's to assess the evidence that we have. So what we want to do is we want to figure out how likely it is that we would observe the data that we saw if we assume our null hypothesis is true. So notice how likely implies we're going to calculate probability. So using the chocolate ice cream example that I just kind of threw at you, if I saw that 60% of my sample chose chocolate ice cream as their favorite, what I'd want to calculate is the probability of seeing a sample of 60% if I assume that the population proportion is 50%. So that's what we're doing in a hypothesis test. And we'll get into all of the math of all of that stuff later. So we look at the evidence. After we've looked at the evidence, we come up to a conclusion, and this is the fourth step. So if we find that it would be extremely unlikely to observe the data that we observed, what we actually have. So extremely unlikely means we have a small probability. Then we have strong evidence against the null hypothesis, and we reject it in favor of our alternative. So if I find that the probability of observing 60% of people want chocolate ice cream, if I assume it should be 50%, that probability, if I see that that probability is really small, then I could say, yeah, 50%, that's not correct. It has to be more than 50%. However, if I find that it would not be unlikely to observe what I observed, then we do not have strong evidence against the null and we cannot reject it. So if I don't find that the probability is small, then I can't say that the proportion of people that would pick chocolate ice cream is more than 50%. So let's look at how we set up this hypothesis test. So there are a lot of different hypothesis tests that you can do. We are going to focus on testing the parameters mu and p. So there are a few different types of tests that we're going to look at. So what I have in this chart here is the type of test, what the null hypothesis looks like, and what the alternative hypothesis looks like. So the first type of test we could do is a right-tailed test. So in a right-tailed test, the null hypothesis, HO, has the parameter that you're testing, so either mu or p, equal to some number. So that would be p equals 0.5. 50% of people pick chocolate ice cream. Or mu equals 12. The mean number of credits that students take in a semester is 12. The alternative hypothesis would be what we want to prove. So HA colon, the parameter, same parameter from the null, is greater than the same number that we put in the null. So for the chocolate ice cream example, it would be HA is P greater than 0.5. I think the proportion of people picking chocolate ice cream is greater than 50%. Or I think the mean number of credits that students take is greater than 12. The next type of test is a left-tailed test. The null hypothesis is set up exactly the same. HO, your parameter, mu or p, is equal to a number. The alternative is very similar, but now in a left-tailed test, your parameter is less than that number. So this would be if I wanted to say that the mean number of credits that students are taking is less than 12. And finally, we have a two-tailed test. The null hypothesis is the same. And in the alternative hypothesis, we say that the parameter mu or p is not equal to the number. So the proportion of people that are choosing chocolate as their favorite ice cream is not equal to 50%. So let's look at an example. The mean annual rainfall in Arizona is 8 inches per year historically. However, weather researchers are interested in whether this amount of rain has decreased in recent years, leading to drought conditions in the state. Write a null and alternative hypothesis for this situation. So some things we want to identify in this problem before we write the null and alternative are: what parameter are we looking at? So in this case, we are looking at the mean. The mean annual rainfall. We also want to determine what is the rainfall historically or supposed to be, or what have we been told it is. And historically, that mean was 8 inches per year. So from this, I can come up with my null hypothesis. My null hypothesis would be HO mu equals 8. So I'm going to start my hypothesis by assuming that the mean rainfall is still 8 inches per year. Now for the alternative, I want to look at what do the researchers think is happening? What are they trying to prove is happening? So they're trying to prove that the rainfall has decreased in recent years. So decreased means less than. So my alternative would say HA mu is less than 8. And this becomes a left-tailed test. Look at another one. The Kelley Blue Book price of a used Chevy Corvette is $86,012. Grant wonders if the mean price of a used Chevy Corvette in the Denver area is different than $86,012. Write a null and alternative hypothesis for this situation. So again, we are looking at the mean. The Kelley Blue Book price is the price that we are going to use for our comparison. And then Grant wonders if it is different in Denver. So the null hypothesis would be mu equals 86,012. And the alternative would be mu is different from or not equal to 86,012. One last example. The Medco Pharmaceutical Company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experienced headaches as a side effect. A researcher for the FDA wants to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. Write out a null and alternative hypothesis for this situation. So 2% are experiencing headaches. I have the word percentage again. And they want to know if it's more than 2%. So the word percentage is an indicator that I'm going to be testing the parameter P for proportions. 2% is what we are comparing it to, because that's what that's the percentage experiencing headaches on the competitor. So they want to see if their antibiotic is more than that. So the null hypothesis is P equals 0.02. We always want to write out our percentages as decimals when we're writing the null and alternative hypotheses for proportions. And then the alternative is P is greater than 0.02 because of the more than statement. And this is now a right-tailed test. So the last thing we're going to talk about are errors, type 1 and type 2 errors. So whenever a hypothesis is performed, there's always a chance that we come to the correct decision and a chance that we come to the incorrect decision. We may never know whether we've reached the true correct decision or not, but it's something that we have to keep in mind when we're performing our tests. So there's always a chance for false positives and false negatives. So the potential incorrect decision in hypothesis testing are called errors. And we have different types of errors based on the type of mistake we're making. So whether it's a false positive or a false negative. So making our decisions, what I have here is a table that I've set up to help us kind of break this down. So the first one we're going to look at is where we do not reject HO. That's the decision we made. And the reality is that HO is actually true. So 50% of people prefer chocolate ice cream, and we came to the conclusion that we should not reject that hypothesis. That is the correct decision. If 50% of people prefer chocolate ice cream, and we come to the conclusion that 50% of people prefer chocolate ice cream, that's the correct decision. The next one, I don't remember which one I did next, so we're just going to click the button and see. Okay, is the other correct decision. That is where we choose to reject the null hypothesis, and the null hypothesis is actually false. So more than 50% of people like chocolate ice cream, and we decide, and our test says more than 50% of people prefer chocolate ice cream. So now let's look at the incorrect decisions. A little bit of a spoiler. The other two are incorrect. So I believe the one that I did is the bottom right. Yes. So if we decide to reject the null hypothesis, but the null hypothesis was true, this is a type 1 error, also known as a false positive. I'm going to go to the next one, and then I have an example. So let me just go through this. Okay, so then the other type of error is a type 2 error. This is where we come to the conclusion that we should not reject the null, but the null was actually false. Type 1 error is represented with a symbol known as alpha. This is a Greek letter. And then the type 2 error is represented with a symbol known as beta. This is another Greek letter. As you increase the chances of a type 1 error, you decrease the chances of a type 2 error. If you let me phrase that differently. I'm so sorry. If I want to decrease the chance of a type 1 error, I'm going to end up increasing the chance of a type 2 error. If I decrease the chance of a type 2 error, I increase the chance of a type 1 error. So the balance is to decide which one is the one I want to minimize. And that's not really something we're going to get into, but again, it's something that we always want to keep in mind as we're running hypothesis tests. So an example that I wanted to show you guys with the table is a null hypothesis where you do not have COVID. And the alternative is you do have COVID. And this is a great example because we take a test for this. We walk around every day assuming we do not have COVID. And then we start to get a little tickle in our throat and we go, ooh, maybe I should take a COVID test. Maybe I should assess the evidence that I'm getting sick and do a test and see if I should reject my assumption that I don't have COVID based on the test and determine if I do have COVID. And this is also true with flu tests, pregnancy tests, any sort of medical test that we take to determine if we're sick or not. But COVID tests have just been very prevalent in our lives for the last few years, so I thought it would be relevant. So what do these things mean? So if we do not reject the null hypothesis, that means your COVID test was negative. If we do reject the null hypothesis, that means you tested positive. The null is actually true. That means you do not have COVID. Regardless of what the test says, in all actuality, you don't have COVID. You have a cold, an upper respiratory infection, bronchitis, the flu, anything else that could be making you feel the way you feel, allergies, who knows what. And then HO is actually false. You have COVID. You got it, babes. So if you actually have you do not have COVID. HO is actually true. And you test negative. That is a correct decision. Love that for you. Okay? You don't have COVID and you tested negative. Awesome. Go figure out why you're not feeling good. Maybe you just need some sleep. You actually have COVID and you test positive. That's a correct decision. Don't love that as much for you, but I love that you know that you have COVID. And now you can sit at home and not be around other people and get better. The things that we don't love so much. Okay? This type 1 error. You don't have COVID, but you tested positive. So now you think you have COVID and you're calling off of work and not going to school, but you maybe didn't really need to because maybe it was just allergies. But the test was like, you got COVID, babes. Not the worst. Definitely inconvenient, however. And then the type 2 error. You have COVID, but you took the test and it came back negative. That's a problem. Because now you're walking around like, oh, it's fine. It's just allergies. It's just a cold. But it's not. It's COVID and you're spreading it and you don't even know it because you did what you thought was the responsible thing and you took a test. And the test was like, you're good. Drink some water. Blow your nose. That happened to me. I felt like I was on death's door. I knew it was COVID though, even though the test said it wasn't. I knew it was. So I still stayed home. Anyways. So these are things that can happen when we do a hypothesis test as well, that we just always want to make sure we're aware of. So just like when we take a COVID test or a flu test, we don't always know, is this a false positive, a type 1 error? Is this a false negative, a type 2 error? Was this correct? We just have to trust it. And it's the same thing with hypothesis testing. We just got to trust it. We got to trust that we did everything we were supposed to do and that we've got the correct results in the end. Or we repeat the process, which we do with COVID tests as well. Sometimes you take more than one test if you're not sure. And sometimes you repeat the hypothesis testing process if you're not sure. You get a new sample, you do it again. So that is our introduction to hypothesis testing.